Okay, so welcome to the second morning session. Our first speaker is Matteo Sfragara from University of Padova, and he will be talking on competing growths on configuration models. Okay, Matteo.
So thank you for inviting me. It's a pleasure to be here. After 6 years, last time I was in India was 2020. With my PhD, I spent 3 years coming like every time for a month, visiting ISI Kolkata, and also I came to Bangalore. And it's nice to be back after 6 years and see some faces that I know, some faces that I don't know. It's been a nice workshop. So I'm talking about networks today, and I'm giving a big overview about a lot of the results for competition on configuration model. We'll see what it means precisely in a bit. And we will do it in different ways. We first introduce first passage percolation and understand what this model is and how infection can spread on a random graphs through first passage percolation. And this is work that I did during my postdoc time already a few years ago. And now I'm picking this up again, adding some extra extensions, in particular long-range jumps. So I'm bringing this model up again. This is still ongoing work, but I felt like it's nice to talk about this. So just some faces to show who I've been working with. So during my postdoc time, I was at Stockholm University. I was working with Mia, Dave, and Remco. We worked a little bit on this first passage percolation competition on the configuration model. And now in Padova, I'm working with Bernardo, trying to add this long range phenomenon. So let's give a little bit of introduction, general introduction on the first passage percolation model. This has been somehow introduced in 1965, quite some time ago, to model some flow or fluid through random media. And it's basically defined in a simplest version on the lattice. Let's think of ZD. And on the edges, put some non-negative random variables. And we call them passage times. Those is omega E are on the edges. There's also a version where the weights are on the vertices, but we'll focus on the edges right now. And then we can, of course, have a metric, and a distance is defined distance between two vertices as the fastest way to go from U to V. So it's the minimum over all possible paths from U to V of the sum of all the weights that you pick. So that's first passage percolation, the fastest way to go from point U to point V. This minimal weight path is also called geodesic sometimes. And so this is the classic definition on ZD. In particular, this has been studied a lot with exponential passage times, and this is called sometimes in the literature also as Richardson model. We are interested in studying a little bit better how this type of spread of infection in a network can compete when you have multiple infections started in a network. But first, before going to that, I want to give a little bit of a brief overview about major open problems in this area. There's two big areas of two big topics. One is shape theorem and one is fluctuations of the travel time. So shape theorems is basically trying to understand what happens when I let this infection grow from the origin of my lattice and I rescale it linearly. And this B of T, this ball, this cluster of vertices that I managed to infect within time T, if rescaled, should converge to something. And it's not really clear that's something, what it is. We know it's compact and convex and not much more. We don't know if it's differentiable. There's big open problems since many years in the literature. And another open problem is about fluctuation of T. T is the travel time. So imagine this is the origin, then you have a point at some point here. It could be in any direction in space. Let's think horizontally. So T is the effective travel time that I need to go along the fastest path, geodesics. And it's believed to more belong to the KPZ universality conjecture from Parisi Zhang, in the sense that it fluctuates around its mean with order n to the 1/3. And the geodesics itself, so the path itself, will also fluctuate transversely, vertically on scale to n to the 2/3. So these are all conjectures, these big open problems. And another big problem is what is the variance of T? Give polynomial upper bounds on this variance would be very nice. So far, the best we can do is n the log n, but of course we should get something polynomial in n if we believe in the KPZ conjecture. So these are open problems. I've been working on some version of these also in other work during my postdoc time. I'm not going to talk about that. It's just to give you a flavor of how big this field is and how interested people are. So what we want is, forget the lattice, we want to work on networks. And when we work on networks, there are two important things to consider. One is the topology of the network. If there is many edges, if there is short paths, so you can have small word networks or ultra small word networks. Distances are different, and depending on the distances between vertices, also first pass of percolation behaves in a different way. So the topology is one crucial element, and the other crucial element is, of course, the variables that you put on the edges, the passage times. If all of them are equal to 1, we have graph distances. But if they are random, then we want to know, okay, what's the fastest path, how long it takes to go from U to V. And in general, this question are studied on different type of models, complete graph, also some random graphs with exponential passage times, or also more general passage times. We will focus in our setting on the configuration model. So I will just introduce a little bit the configuration model, but we've been talking about this already in these days. So I think everyone knows what we're talking about. Let's start with IID copies of a random variable D. Let's take D1, Dn. These are the degrees. This random variable D has a certain distribution, and we want it scale-free with a power law tail behaving in this following way. L is a low, slowly vary function, but it's not really important. The important is the power and the exponent here. There is this tau that basically determines the type of topology that we have. The model is, as you know, you pick n vertices, you assign half edges depending on this degree distribution, and then you just match them uniformly at random 1 by 1 or 2 by 2 until you're done. And we have a random graph, a realization of a random graph. Depending on this tau, we have different regimes. So if tau is bigger than 3, we have a model where the degrees have finite mean and finite variance. If tau is between 2 and 3, we have a model with finite mean and infinite variance. And if tau is between 1 and 2, we have a model with infinite mean degrees. So the topology is very different. Here, there is some high degree vertices that basically decide everything. And there's like a small hub of high degree vertices that makes the most of the total degree, while here we have more like homogeneous settings. There is also some assumption that guarantees the existence of a giant component. Just gonna go quickly on this, but we want a giant component to exist with high probability, which means we want all but a little of n vertices to be in a giant component, because then competition ensures that you are kind of conquering almost all the network. And depending on the regimes, we have some basic assumptions on the degree sequences that guarantee this. Let's not really focus too much on this. But what we want to introduce now is the competition I've been talking about. So what does it mean? It means that there are 2 infection types. We call it sometimes type 1, type 2, or blue and red. And they spread at the same time on the network, and possibly they can have different passage times. So there is a family of passage times for type 1 and a family of passage times for type 2. They could be different. We start from 2 vertices, choosing uniformly at random. It doesn't matter because there is exchangeability in this type of model. So really, whatever 2 vertices you pick, if they are uniformly at random, the model is well defined. And then you start spreading along the edges of these 2 vertices. You go to nearest neighbor spreading, basically. When you reach a vertex, if you have reached a vertex and this is not infected yet, then you infect the vertex, and this vertex becomes immune to the other infections. So once you color a vertex red, then it stays red all the time. So as I said, some basic assumption depending on the regimes ensures that there is a giant component that comprises also almost all vertices. So at the end, this model is well defined. You can talk about, okay, how much of the networks have you infected? And we are interested in one simple thing: is there coexistence or not? In the sense, is it possible that both types occupy the positive fraction of the vertices at the end? Or is it going to be the case that one takes all the networks and the other one takes only little of n nodes? There is n nodes, so if at the end both take linear linear in n order of nodes, then we have coexistence. Otherwise, one wins and the other one loses. So in the following, I will show some results. This is the notation I will use for now. And I is like type of infection, 1 or 2, type 1 or type 2, red or blue. So NIN is the final number of vertices. When I put the bar on top, it's the proportion of vertices infected. This is always at the end of the process. So you let the competition go, and at the end you observe. And losing means the number of vertices of the loser. So there's a little simulation I want to show first to just give you a flavor. Go here. So this is from the network pages, which is a website that we use in the Netherlands a lot, where we have a lot of simulations of all type of phenomenon and processes on networks. This has been done by colleagues in the Netherlands, Robert Fichtner and Martin Gozens. And I'm gonna just realize a network. This is like 150 vertices with a certain parameter tau 3 between, I put 3.2. And the edge passage times in this case are constant, so they are not variables. You'll see the spread going around precisely at a constant moment, but this is a little bit not nice. Let me put 100 nodes. Okay, let's say that this is a network. Then I choose one node here as the first starting point of infection 1, and then I choose another node here as the first starting point of infection 2, and then they start spreading along the edges. Now the passage times are constant, so they go to the same speed. At some point, blue reaches a hub or a high degree vertices, so you get an advantage. And at the end, you can see on the top right the count of nodes that are infected. So it is like 88 blue, 18 red, so blue wins. Of course, when we are interested in phenomenon like this, when n goes to infinity, but this is the idea, with the only difference that the passage times are not constant, but they're random. This is fake. This is just for simulation. It's just to show and give an idea of what happens. We never have that in reality. We arrive at this. But there are situations in which you could reach a vertex at the same point. It depends on the degree. If the passage times degree distribution is discrete, it's possible, for example. Then you have to decide that there is a rule maybe and decide, but this is going to effectively change the outcome of the competition. So not very interesting. Okay, so let's focus on the case with finite variance, which includes the case with tau bigger than 3. Exponential passage time of different rates, lambda 1 and lambda 2 for the two types. And there is a theorem and a work by Albert, Deifen, and Jansson in 2019 that shows that if the two intensities are the same, then the proportion of vertices of type 1 converges to a random variables with density on 0, 1, which means that also the proportion of vertices of type 2, which means that there is coexistence. They're both getting a linear fraction of the vertices. If one is smaller than the other one, the smaller one loses. The smaller one converges to 0. So this is saying if they have the same intensities, there is coexistence. Otherwise, one of the two takes almost all the networks and the other one loses. You can also conjecture how big is the number of vertices that the loser gets. It can still grow to infinity, but still little of n, because lambda 1 over lambda 2 is smaller than 1. And in general, you could do this for not only exponential passage time, for more general passage times. And what you do is you approximate with branching processes, but they are not Markovian in this case. So there is a little bit of more work to do. This is not precisely been done, but this is what we think, and a little bit of heuristics of how this is proved. It's basically there's an initial phase where the outcome of the competition is determined, and then the proportion remain the same. So everything happens at the beginning, and then at some point it stabilizes. And the proof is basically exploring the graph together with the infection simultaneously from both types, and then keeping count of how many half edges there are of type 1 or type 2, and somehow keeping count of the proportion of them. And it can be shown that the number of active half edges after k steps can be defined in this way. And this behaves as a martingale. And then depending on the speeds and the intensities, in one case, we have that somehow it converges to a constant limit. And then there is coexistence. In the other case, we show that one dies out and the other one takes everything. Is more or less how it goes. So there is some exploration and branching process approximation to understand what's going on in the network. Finite mean and infinite variant, case we tau between 2 and 3, similar but not the same. Still exponential passage time. This is work of Remco and Nathan. And here he's saying something different. It's saying the proportion of number 1 at the end, it's an indicator function. It's either 0 or 1, depending on some variables. But that means that there is no coexistence. One of them is going to take everything, but it's not clear which one. It doesn't matter. It's not the one with less intensity is going to lose like before. Both could win. The proportion either go to 0 or 1 at the end, but it depends on some variables, and these variables are shown. There are explosion times of continuous time branching processes that you use again to analyze somehow the networks. This phenomenon is called the winner takes it all, in the sense that there is one winner takes all the networks except of little of n nodes. But remember this because we're going to come all the rest of the talk about this phenomenon. Again, little heuristics here, just showing that. Okay, at the beginning, if you take two vertices uniformly at random, these are probably distant. So you can think of the evolution at the beginning as independent branching processes, and you're going to follow them. And then at some point, you check the explosion times. And depending on who explodes first, that means they reach very high degree vertices, then you get the lead. But this doesn't depend on the rate, it depends on the process itself. So any of the two could win, but then once it gets an advantage, the other one cannot catch up anymore. So the winner takes it all phenomenon is what's going on, different than before. So first regime was like the loser loses, the one who is less strong loses. Here, both of them could win. Let's go in the third case. This is the work I've been doing, and it's even stronger because you have now infinite mean. So you have a very specific topology of the network. When you have very like, we'll show it soon. We have like a hub with the giant degree with high degree vertices, and then everything else is connected to that. There's a very particular topology. And for general passage time distribution, we have that basically the loser doesn't even move from the starting point. The winner takes all the graph. It's the winner takes it all phenomenon, but it's even stronger. We call it the winner takes it all but one. The loser doesn't move at all. And who wins? Again, any of the two could win, depending who makes the first move, basically. So it's even strong. And again, I have a simulation showing this phenomenon, but probably it's not going to work. This is a very specific. This is happening when n goes to infinity, but if I I take tau between 1 and 2, for example, 1.3, and I take 150 vertices, you have this very dense, not really dense, it's just a few nodes with high degrees, and everything else is connected to them. So if I just pick two random nodes like this one and this one, should be a much more somehow intense spread in the sense, okay, didn't work very well, this one. Try again. Depends on the nodes to pick up, but the idea that one of them reaches a giant at some point and the other one is blocked. Okay. Maybe simulation is not very good, but the idea is, okay, you just quickly hit the core and then you're blocked. And we show why in the next slides. So a little bit of how it goes. It's just about the topology of these networks. Total degrees of the network scales in a certain way as n to the 1 over tau minus 1. This is easy to understand, just basic computation. And also the maximal degree scales in this way. So all the contribution to the total degree is given by the nodes with maximum degree. So the idea is to split the vertices into two sets. We call giants and normals. And we split it in a smart way in the sense that giants are the nodes with degree above a certain threshold, epsilon n un. Un is this total degree. So epsilon n is they can go into zero, but in a way that basically the giant nodes are finite. There are few of them, and they are highly interconnected with each other. And they form a complete graph between each other with a lot of multiple edges between each other, which is the real hub and core. And then everything else is over there. There are n nodes, basically, all the things outside. Then the degree is quite smaller. The total degree is something that goes to infinity still, but in a way which is lower than un, which is the degree of the giant. So if you take a vertex uniformly at random, this is with high probability connected only to giants. And this is a big idea of the network. So you take a vertex outside, this is with high probability, all these half edges goes to something inside the giant core. Graph distances are very small, basically, because if you are connected to the same giant, then you have distance 2. Otherwise, you are distance 3 because you're connected to two different giants, and then giants are connected with each other. It's a very extreme topology. And between giants inside the hub, you spread very fast because there is a lot of multiple edges going to infinity. There is like actually order UN, which is of this type, going to infinity edges. So the spread is really quick. So the idea is the first one who moves from the beginning hits a giant, and then the giant goes to all the giants, and then from there, the other one cannot move at all because it's blocked. Very, very strong. Okay, some variations of these models. Multiple starting points. If you, instead of starting from one type 1 and one type 2, you start with ki vertices of type I. Again, winner takes it all except of the initial vertices of the losing time. So we have this strong winner takes it all phenomenon. If you consider the arrays configuration model, so you remove self loops and multiple edges, again, the winner takes it all but one, strong phenomenon, because the topology is quite strong. If you condition the configuration model to have degrees smaller than certain power of n, then of course, in some specific values of this alpha, you say n to the alpha, for some specific values, and you can understand how distances work in the model. And then again, we have the winner takes it all but one, very strong phenomenon. Stronger condition, if you condition even more, for example, something not as a power of n, but something a little bit less, depending on what this an is. If you condition an to be very small somehow, then you can see that the loser can get more than one vertex. You can see that the loser start going out. It's just basically cutting all the high degree vertices, so it becomes more similar to the other regimes. But the idea is this phenomenon is quite robust under different variations. So the only way to get rid of this phenomenon is just really to either put some constraints on the degrees, or maybe play with different type of passage times. So the idea is, okay, all this variation of the models, arrays, conditioning, multiple starting points, they all show that topology is quite strong. So the winner takes it all but the initial point. And I'm not done. There's just some references for this part of the talk. Just to show, okay, this is the type, the model with tau bigger than 3. There's this paper that's been done that I showed before the result. With tau between 2 and 3 has been a little bit more study with constant passage times also, and random passage times. And with tau between 1 and 2, this is the regime I was talking about, where we studied this strong, the winner takes it all but one phenomenon. Okay, so now I arrived in Padova last year, and I was talking to people in Padova, and then we are interested in some cybersecurity modeling with some of the people. And then we understood that this type of model could serve as a model for cybersecurity, because in cybersecurity, you could have attacks or malware spreading through computer networks, both through local connections and through random global interaction, like phishing emails or some shared platform online. Like in the cybersecurity world, you have local spread and also global spread. The idea was to model something bigger at the beginning. I will talk about this maybe later for half a minute. But first we decide, okay, but let's understand what's going on first in a single model when we have one random graph, competition, and you allow also long-range jumps, which is somehow modeling the global interaction. So we still work with the last regime with the strong topology, and we see that this changes already a lot in this setting. And we introduce a rate, gamma n. Basically, each infected node can jump at some point to a uniformly random node and infect this node, if this node is not infected yet. So there is a local first passage percolation spread, and there is this long-range jumps. Two type of infection mechanism. Of course, you have to understand how they compete with each other somehow and who wins depending on this rate, gamma n, of course. And we want to understand, okay, what's the overall infection time scale? Is this changing this idea of winner takes it all / coexistence phenomenon? So we're still working on this, and we have some first results.
Matteo, can I ask a question?
Yes.
Why are you taking it such that it can jump to any vertex? Wouldn't it be more natural that it sort of has a certain distance to which it would jump, so it would jump in a ball with a certain radius?
It could be also other variation. We were thinking like when you send like phishing emails or you do like some random malware virus attacks, you don't know who you get. You just hope to get something. You just hope to hack or infect something in the networks. And the idea was to model really like this first, and then maybe you could try to understand different variants. But I haven't seen anything like this in literature where you combine long-range jumps and first passage percolation. So we'll try it with one model, and then we'll see how easy or difficult it is, and then we'll see what to do.
From different points, last time you had a KI with type I. So instead of jumping, you consider I'm starting from there. I remember in your last.
Okay, but then, yes, but then all of this, you could have multiple starting points, but you have to think every time you infect something, this keeps jumping. But also the total amount of first passage percolation power increases depending on where you jump. If you jump to a high degree vertex, then you can percolate quickly to the rest of the graph. If you jump to a low degree vertex, then maybe it doesn't have much. But the model with the initial starting point, with multiple starting points, this has been studied when both of them are fixed, or one of them grows to infinity and the other one not. But if both the number of initial starting point grows to infinity, then you have to understand what's the real passage time distribution is to really know what's going on. So this is a little bit different. Is it clear, more or less? 2 more minutes. So results are following. We identified a threshold. If the rates are not so fast, this is a threshold. It's like we have still the winner takes it all phenomenon, not the winner takes it all, but one, the winner takes it all phenomenon. So one of them gets all the networks except of a little of n node. If the rates are big enough, so the jumps are happening quite fast, then there is possibility of coexistence. This didn't happen before. The coexistence was never possible in this type of models. If you introduce jumps that are above a certain rate, then you can really somehow forget about the network topology. The jumps are taking over. Gamma is the rate of jump. So any infected node just have this rate and jumps, and then it selects a uniformly random node, and you can infect. Yes. The rate is exponential with these like Poisson clocks. So we identified extreme regimes when gamma is very, very small, much smaller than these. We have again the winner takes it all but one. So you're really behaving like the jumps are so slow that it's like if they're not there. And this 1 over log n comes to the fact that if you infect at some point the giant hub, we call it HN, then from there you can go to the rest of the networks, and it takes time over a log n to get all the other nodes outside. So if you're even smaller than that, then it means that jumps are not even fast to make even one jump. So the loser cannot even jump once because meanwhile the winner got the giant nodes and got the rest. And on the other side, if gamma n is very fast, so it's bigger than Kn. Kn was the total degree of the nodes outside the giants. Then we have that the proportion of vertices of type 1 and of type 2, consequently, they converge to a uniform random variable 0, 1. So there is coexistence, and this is completely determined from the jump process. You can couple this with a Foley-Owen model somehow. Jumps are so high that the topology of the network is not important anymore. You're just jumping randomly, and you can couple this with a Foley-Owen. So these are extreme situations. We don't know if these are tight. Maybe there is different thresholds that still work, but for sure below this threshold and above this threshold, we have these two extreme regimes. But the main threshold, the main phase transition is between the subcritical. So I want to give a few minutes, few ideas of how we're thinking of this. So now I introduce a new notation. When I introduce T, to say that I'm counting the number of vertices at time t, because I want to track somehow the evolution of the process. It's the same notation as before. With the bar is the fraction, without the bar is the number of nodes. There is a time t. And then I'm going to introduce this 18 times tau n of f. F stands for FPP, first passage speculation, is first time I infect a vertex with first passage speculation. So the first time I perform an infection through nearest neighbors. And tau n of h in the first time that I hit giant set. These are two hitting times. And I can show that with high probability, I hit the giant set before or at the moment I do the first passage speculation jump. It's very unlikely that I jump that I do a first passage speculation infection and I don't go in the giant set, because we know that all the nodes are connected to the giant. And there are two specific situations inside this less or equal. So there is a possibility where they're equal. That means that the first time I do an infection, I enter the giant set. The first time I do an infection with FTP, I go inside the giant. And there is a possibility that I could enter the giant with the jumps. So I could already be in the giants and I still haven't performed any FTP situation. But if you think about this for a moment, we can show that it's enough to study the process until the first FPP infection. And when we know what's going on at that time, then we know the outcome of the competition. Because if at this first FPP infection, so if at time tau f, the proportion of nodes goes to 0 for any of the two, so that means that they start jumping around, and at some point one performs an FPP infection, but meanwhile the jumps have been happening, so nodes have been infected of the two colors. If one of the two in proportion goes to 0, then at some point one of the two is going to hit the giant hub and takes the rest of the network, but the one who doesn't hit the giant hub stays little o of n. So the winner takes it all. So you can already see that at the moment. While if you can see that they already have a linear somehow fraction of the vertices at time tau f, it means the jumps have been quite high, and they already conquered a lot even before performing an FTP infection. Then we know the coexistence occurs because they already have linear number of. And this is enough to study until this time tau f. And the nice thing is about this time, this is the first time I perform an FPP infection. That means up to that time, I'm only jumping. So then the process is nice because I'm only jumping, and you can study it as a stochastic process with jumps. And of course, then the rate of jumps increases with time because every time I go to a new vertex, this vertex also jumps, but it's nicer to study. And so this doesn't give an idea of the threshold, but the idea of the threshold is given by this. So if we want to compare somehow what's the total jump rate and what's the total FPP rate while I start infecting vertices around. So the jump rate is just the number of infected vertices, k, at some time. times the rate, gamma n. While the total FPP rate is the sum of the degrees times this lambda is the FPP exponential rate. It will be different for the two types, but for now, it doesn't matter. And this is the sum of the degrees that I'm going to jump to. And this can be considered IID. And we can show that. And this there's a given by the degree distribution of the configuration model. So we can show that this sum behaves in this way. So we want to compare the total jump rate and total FPP rate. And when are these comparable? These are comparable when I have reached this number of critical nodes. So after I have infected this KC critical nodes, then it means that the two rates start competing with each other. So the two mechanisms of infection start competing with each other. So now in the threshold of subcritical regime, if gamma n is smaller than the threshold, then this KC is going to be little of n. It means that the two rates are comparable, jump and FPP, but I haven't infected them much yet, just little of n so far. And then at some point, one of them reaches the giant and gets all the networks, and the other one stays little of n. So the winner takes it all. If gamma n is high, that means I've been jumped a lot, meanwhile. And then that means that when the two rates are comparable, the jumps and the FPP rates, then I have already infected order n nodes. And then basically there is coexistence. So this is the heuristics. We have to formalize this properly, but we believe this is the situation. Last slide is the following. So there might be additional phase transition within these regimes, and we want to try to identify them in the sense that, okay, there is the winner takes it all but one phenomenon, so the loser just gets one, but then at some point we can find a threshold at which the loser gets some finite number of nodes, or the loser gets infinite number of nodes, but still loses. It depends on the gamma. And then also in the supercritical regime, we have the situation when, okay, the winner, there is no winner basically. They're both getting linear and nodes, and they behave as a polyurn if we have the extreme regimes where the jumps are very high, but there might be a different situation in which they both coexist, but we could maybe identify proportion of vertices that they get. And then the next project would be to extend all of this to the other regime of tau, with tau between 2 and 3. This is with tau between 1 and 2, with the network topology is quite strong, so it allows us to understand a little bit better what can go on with tau between 2 and 3. The approaches for competing first pass speculation were all about branching processes exploration. We cannot do it with infinite mean, but when the mean is not infinite of the degrees, then we can do branching processes. How would that extend to that setting? We have not even thought about that, but we would like to at some point address this. And then the application I was mentioning before is because we wanted at the end to think of multi-layer networks where each network is a random graph representing a country or a certain specific setting in cybersecurity. And then within that networks, you can have FPP and things spread, but you can also infect through networks via jumps. So you can also infect long range distance. That's why we wanted to understand at the beginning, okay, what if we have a big system with many networks, each of them is a random graph and they interact with each other through jumps, and locally they spread to FPP. So, but this reduces to first to understand what's going on with one model, and then we could maybe put it together and maybe even add some queue in theory and understand how the flow of malware propagates between networks, between different layers. So this is the initial motivation that we had, and then we tried to reduce the problem to first understand what's going on with one random graph, because we haven't seen this in the literature, so we wanted to somehow give it some time and work with it. So thank you.
Questions?
It's possible additional phase transitions. I would rather expect that when you say, okay, you go from you winner from all or finite, but that the finite would just be at the critical value, that this is not going to be a whole region, right? Because that sounds a bit bit impossible.
No, but what is the precise critical value? I mean, from 1 to finite, it's not.
Yeah, maybe even something
Here.
random, right?
Yeah, maybe because I gave this extreme situation when I know there is just one, the loser gets one, but doesn't mean that's the right threshold.
Question. So, if I understand, you have looked at the spatial final configuration, right? Like, but there are dynamical questions also. How do you reach them that are hidden even for the process without long jump? I was wondering if the passage time are no longer exponential but are in heavy tail themselves. I think the result would be stable, the same, but dynamically you will have. How long does it take to conquer the entire universe or to?
The time it takes to infect the network.
Huh?
The time it takes
yes.
for infection.
So there are different results.
Most of the competition results are about coexistence or not coexistence. But there is at the end, how. But there is results about how long it takes to go from U to V. Like what's the minimum passage times.
So if you have heavy tail weight,
not in a competition setting, but just in a one type infection.
Except for in case where pause between 2 and 3. There are subtle things around.
Thank you.
So for this problem with toying between 2 and 3 with long-range jumps or reinfections or something like that, but my guess would be that the critical value would be a positive value. Am I right there? Or so if the rate at which you do a long-range jump is positive, but you could still have the same effect as if you don't have it.
I don't know. I haven't.
But it should all be related to when you reach the hubs.
You don't need to have a rate so high, probably,
Precisely.
to counter effect the topology. The topology is not that extreme, but I don't know if it still should grow. You think it should be? I don't know how it should grow.
I think you're already going to have an interesting behavior when it's constants, when it's a constant.
When it's constant, the rate. Yeah. Okay. Have you thought of this ever? No.
Really?
Yeah, so this uniform jump makes me think of PageRank. This uniform jump makes me think of PageRank, but of course the process is different because in your case it's infection and in the case of PageRank it's random walk. But still, I was wondering, is there any analogy with like random walk graph with such random jump?
I never really thought in that direction. Because I haven't seen any work where we are spreading and competing with jumps. So we're basically starting with new ideas or trying to understand, but I haven't looked in the random walk area. And I don't know if it can be applied, it would be nice, but
Okay, that is interesting.
So what you call jumps is the spreading on the complete graph, right? At a rate gamma n. If I want to
jump is like I'm infected and I jump uniformly at random and I infect something uniformly at random. It's not the nearest neighbor.
Sorry, this is a different question. So, like you said that the weights throughout our IID, right? In like whatever among the community, whatever. Yes. Like. So, has there been any work where the weight depends on the topology of the graph? Like they're independent, but
yes, everything I've seen is
for spatial percolation there is where the edge traversal time, let's say exponential with a rate depends on the decreasing side.
Okay. But here, for example, like you could try to block the hub with sort of weak conductance. Yeah.
Yes. Yeah. Okay. But not in a competition set.
So, is it in essence same to the model where to begin with, you just put some uniformly at random edges with like 0 weight? That's something you are doing basically, right? But in a dynamic way. So,
with edges with.
So you like take some like disconnected edges to begin with, and like you put 0 weight on those edges. So you choose some edges which are not connected to begin with in the configuration model, and just put 0 weight there. So basically, that's what you are doing in a dynamic way, right? Just connecting to edges with 0 weight, so that you just
The jumps, you mean?
yeah. So taking a jump.
It's a complete graph underlying, and everyone is connected to everything somehow. So you can potentially reach anything you want. But then these jumps have passage times, which is
yes, but
gamma n over n, because you are uniformly choosing one of them.
But for these jumps, basically your weight is 0, right? You just instantaneously go there. That's
yeah, but you have to wait to jump somewhere.
Sorry.
If you think of an edge, you can put the passage time with the rate gamma n. It's the same thing.
It's the same thing.
Gamma n over n somehow, but yeah, maybe it's slightly different. But
I was just thinking that if to begin with, you put some like edges with very small passage times, like of a very small order, like 1 by n or gamma by n, that would be a close cousin of this model, right?
we could, I think, interpret this model also in this way that you're saying. I don't know precisely if it's going to be the same, but the idea is you could have a complete graph of edges, all with certain type of weights that represents the long jumps.
Oh, okay.
Instead of I have a vertex and I'm going to weight a certain amount and then jump uniformly around them, I can tend to have connection with all the edges and jump to any of them when I want with a certain weight.
Okay, thanks.
Okay, so in view of time, let's thank Matteo again.